Welcome to week 8. We are in a new chapter, chapter 16 this week. Let's get started. Let's look at a Calc 1 review first of all. Remember from Calc 1 when you looked at definite integrals, that should be in T in there, shouldn't there? Never noticed that until now. And Riemann sums. So here's the basic idea behind this. When you have the integral between 2 and 5 of this function, here's a graph of that function. You start at 2, you go up to 5. Those are my limits of integration. And you want to find that area exactly. So that's what we're going to try to do. I'll erase that. And the way that we do it, the technical way that we do it, is that we break our x-axis into pieces. And the width of each piece we call delta x. And we make a rectangle. And I will make a left-hand sum. So in each rectangle, I will take the left-hand point of the rectangle and see where it touches the function. And that area is an estimate of what's underneath the function right there. And then I do it again with my second rectangle, which I'll make another color. I find out where my left side touches the function, then I go across and down, and there's another rectangle. And I'll take a third one. So here's a third rectangle, and those are all the rectangles I have right now, because now I'm up to 5. That's delta x, and that's a delta x as well. And I find the area of that rectangle, and the sum of those rectangles is an estimate for the area. So we can see in this case it's not a very good estimate, so how do I get a better estimate? I get a better estimate by making narrower rectangles. So here's my first rectangle and my second rectangle. In this case, would still be in the same spot, so there's not a whole lot that's really saved here, but in this second piece, in the yellow rectangle, there's my first piece, and then there's my second piece. And in the third one here, there's not a whole lot saved, but there's a little bit saved on the blue. You can see I saved quite a bit here and quite a bit there, so I have a little closer fit. And the more rectangles I take, the better estimate I get to this area. We can also do this with a left sum or a right sum, which I won't do. Okay, we can do that in class if people have questions. And there is another way to do this if we get lucky, and that is the fundamental theorem of calculus. Okay, so coming back here, what I'm taking is the limit as delta x goes to 0. That's the width of the rectangle. So as those rectangles get skinnier, there are more of them, and I'll take f of x star. X star is something within each of my delta x's. And actually, what's nice about this theorem is it doesn't matter which f of x star I take, as long as it's inside my delta x. So each x star is going to be inside the interval times the delta x. So this is the height of my rectangle, and this is the width of my rectangle. Okay, so that's the technical definition. You might ask why we need this, and the answer is that not everything follows the fundamental theorem of calculus. So sometimes we do need to come back and use this definition. But let's move forward and talk about the fundamental theorem of calculus. It's so fundamental that people usually just use its initials. FTOC stands for Fundamental Theorem of Calculus. And this is what it says. It says, suppose that you have a continuous function. F is a continuous function on an interval, a closed interval. And I'll say that that closed interval goes from A to B. So here's a picture, here's my A, here's my B. It could be a horrible function. It could have all kinds of sharp points, but the idea is that it's continuous. It does not need to be differentiable, just continuous. Okay? And suppose that we have another function, so this is little f of x. That's supposed to be an arrowhead there. All right. And so we also suppose that we have another function called capital F, and it has the property that if I take the derivative of that I get the little f of x. So this is called an antiderivative. If those two things are true, then the area under the curve, between the curve and the x-axis, from A to B, is equal to the big F of B minus the big F of A. There's the fundamental theorem of calculus. Now the trick is finding the antiderivative, and there are plenty of functions where you can't find the antiderivative at all. In fact, the function that is used for the normal curve is one of those functions. It doesn't have what's called an analytic antiderivative. So unfortunately, we do have to go back to the numerical method that we talked about a little bit ago with the rectangles. But when we can find an antiderivative, this is definitely the way to go, right? Because it's very easy. Also, I need to let you know that this is what Newton and Leibniz are known for. So Newton did not sit around and work out the f of b minus f of a, or excuse me, the f of a plus h minus f of a over h. That was known back in the 15th century, two centuries earlier than Newton was around. Fermat knew the definition of derivative. He had worked that out. And finding areas under the curves, we now know that that was known by Archimedes way back, so thousands of years ago. So what Newton and Leibniz found out was this connection between the antiderivative and the area. They found that derivatives and definite integrals are connected. So that's their contribution. Okay? All right, moving on. In a multivariable setting, it's a little bit different. And we're going to start with just a rectangle, but it doesn't have to be a rectangle. So I'm going to take a rectangle in the xy plane, and I'll go from 0 to 3 in the x direction, and maybe 0 to 4 in the y direction. And what I want to find is the volume enclosed underneath the surface over the rectangle. So what I do is I change colors first, hopefully. I break this up in both the x direction and the y direction. So each of these little things is a dx or delta x, and each of these little things is a delta y over here. And I take one of those guys and I shoot it up to make a column. And I find out where it intersects in the curve, and I want to find the volume over that little piece, and I add them all up. So I have a whole bunch of little columns, and I'm finding the volume. So the volume between the surface and the XY plane over the region. And in this picture, that blue rectangle in the XY plane is the region. Okay. So here's the technical definition straight from the textbook. So the textbook starts with a rectangle, as we said. We're going to divide it into sub-rectangles. We're going to make sure that our little function is continuous on that rectangle, so we don't have any holes, we don't have any breaks, we don't have any gaps, we don't have any vertical asymptotes, anything like that. And in each of those little tiny rectangles, we're going to pick a point at random. And so then to find the definite integral, I'm going to move way over here. I'm going to plug that point into the function, which gives me the height of the column, times the area of the base. So this is the volume of each little column. And when I add all those volumes up and then take the limit as both my delta x and delta y go to 0, I get the exact volume. And here's my notation for that. Okay, R is the rectangle, and we write it as two integrals and then the f, and then we either write a dA or we write a dx dy, or we could also write a dy dx, but we'll see that in a minute. That's called a double integral. I can't spell integral today. There, it's the second one. So let's look at an example numerically, and then we'll look at some other examples as well. So we've got a rectangle. X is going to be between 0 and 6, y is between 0 and 1, and it's written out here in terms of some points. I'm going to start to draw this a little bit over here. I'm not going to draw it quite yet, but there's my XY frame. Let's find that area. So the first thing I need to do is cut this into little sub-rectangles. And let me show you how we do that. Change colors. Here's a little sub-rectangle. My x goes from 0 to 0.5, and my y goes from 0 to 3. So from 0 to 0.5, and from 0 to 3. And what these values in the grid are telling you are the height at each of those corners. So at 0, 0, my height is a 5. At 0, 3, my height is a 7. At 0.5, 0, my height is a 4. So this kind of comes down like that. Whoops. Not quite like that. I take it back. Comes down like that. And then at 0.53, which is out here, my height is a 5 again. So this kind of goes up like that, gets much taller. Okay, and 1, 2, 3, 4 sides, so it looks kind of like that. There's the top of this little rectangle here. So I'm going to pick the tallest because I'm looking for an upper estimate. I'm going to pick the tallest point. Then I'm going to use that for my height. So in that first little sub-rectangle, 7 is my height. My delta x is 0.5. And my delta y is 3. So there's my f, there's my delta x, there's my delta y. So the volume of this one little thing is 7 times 0.5 times 3 is 21 times 0.5 is 10.5. Now I'm going to make another rectangle. Let's change the color. Let's make it blue. So here's another one right here. And here's how I'm going to interpret that. When x is 0 and y is 3, that's right here, my height is 7. When x is 0 and y is 6, my height is 10. So that function goes up there. When x is 0.5 and y is 3, my height is 5. That's this point right here. And when x is 0.5 and y is 6, my height is 7. So it comes like that, comes forward, okay, and then it comes up to about a 7. Whoops, farther up, 7's more like that. And then like that. So there's the top of that surface. That's above that. There's my next surface. So its volume is going to be, since I'm finding the upper estimate, I'm going to take a 10. And again, my delta x is 0.5, and again, my delta y is a 3. So that's 30 times 0.5, which is 15. Let's do the other two. Maybe a green. Here's another rectangle. That corresponds to this rectangle down here. And so 0.50, there's my 4. There's my 5. Looks like that. At 1, 0, my height is a 3, so it's shorter, and then a little taller. So that rectangle looks like that, and there's the top there. And again, I want the tallest number, so I'll take a 5 times 0.5 times 3, which is 7.5, and I'll do my last one. Let's make it yellow. That's this rectangle, and that corresponds to that rectangle right there. And I won't draw it. There's my highest point. So 7 times 0.5 times 3, which is 10.5. And then I add all of it up. So 21, 36, 36 plus 7 is 43, so 43.5. And that's my upper estimate. So we know that the volume is smaller than 43.5. Okay, we could also find a lower estimate. We go through the same process, and instead of picking the largest number, we pick the smallest number. It's the only difference. And then the true volume is between the upper and the lower estimates, so I can kind of squeeze it in to get get a good estimate of what the actual volume is. Okay, let's do a little bit of practice. This is the top view of our function. And so the function is actually the z-axis. Imagine the z-axis coming straight out of the screen toward you, right toward your forehead. Okay? Just like in Calc 1, when the function is above the x-axis in Calc 1, we have a positive area. When the function is below, we have a negative area. The same thing happens here. When the function is above the xy plane, our volume is positive. When the function is below the xy plane, our volume is negative. So let's take a look here at this shape and imagine what that surface looks like. Here's my function, xy squared. In the top half of my region, remember this is the floor of my shape, and the function is either above or below it. My x value is positive, and my y value is also positive in this quadrant, right? This is where y values are positive, and I have a positive squared. So I have a positive area in that part of the shape. And if I look down below, down here, my x value is still positive, right? This is the positive x-axis. My y is negative because now I'm below the x-axis, but because I have a negative squared, this is also positive. So this shape, this integral will have a positive value. Now I'm going to see if I can get into GeoGebra, and we'll take a peek at it. If I can pause this video and okay, I think I've got a pretty good picture here. The purple is the function xy squared, and the red cylinder is actually the floor right here. So you can see here's the first quadrant. I'm looking at things that are inside of the cylinder and below the purple, so that's positive. And then here's that fourth quadrant, and again, inside the cylinder and below the surface, so I have a positive number. On the other hand, when I have x squared y, let's see what happens with that. In the first quadrant, I have a positive number because the x and the y are both positive. But down here in the fourth quarter, my y is a negative, and it's not squared, so I should have a negative. Let's change that in GeoGebra and take a peek. So if I erase that whole thing and put in x squared times y, we can see here's the first quadrant. So this is the top of that circle, and you can see the functions above the axis. So we have a positive on that part. Right here is the fourth quadrant. You can see still we're inside the cylinder and above the purple, so that'll be negative, and the two things cancel out. Let's go back to the PowerPoint. Okay, we also have a fundamental theorem of calculus for two variables, and we do what are called iterated integrals. This is due to an Italian mathematician named Fubini. He's a really smart guy. And let me get a nice color here. And here's what it says, is you work inside out. That's it. So let's take a look. If I'm going to calculate this, I'm going to first calculate what's inside. So I'm going to integrate from 0 to 3 xy squared dy. Now, how do I take that antiderivative, you may ask? Here's the answer. Y is your variable, and just like when we took derivatives, because y is my variable, I'm going to treat x as a constant. So this is the same thing as x will carry along because it's constant times 1/3 y cubed, and I want to evaluate it from y equals 0 to y equals 3. And it's very important to write the y equals at this stage, because when you go to plug in, how do you know whether to plug in for the x or the y? This tells you. And that comes from the fact that the dy is on the inside for this particular integral. So when I plug in, I'm going to have 1/3 x, and I'll have 3 cubed minus 1/3 x times 0 cubed, which comes out to be, it looks like 9x minus 0. And notice now I don't have any y's left in the integral. I only have x's. I've integrated out the y. That's how we say it. Or I've integrated the y out. All right? So then when I go to my next step, now, instead of having xy squared dy, I just have 9x, and dx, because that was what was left over after I did my inside integral. And that's very easy to do, right? That's 9x squared, evaluated from 2 to 4, over 2. And I don't have to put x equals at this stage, although it never hurts to do it. It never hurts to do it, but you don't have to because there's no ambiguity about my variable. So I'll get 9 times 16 over 2 minus 9 times 4 over 2, which looks like that's going to be, let's see, 8 times 9 is 72, minus 18, which is 54. And there's my integral. Moving on. We can also undo the chain rule by doing a u substitution. Let's just review from Calc 1. The idea is, for the chain rule, if you have a composition and then take the derivative, that you know you take the derivative of the outside, evaluated at the inside, and then multiply by the derivative of the inside. So when you're doing antiderivatives, you're going to look for one piece that looks like the derivative of another piece. And then you're going to let u be the g of x, the thing inside. Now, that doesn't work unless you see the derivative of that on the outside or something that's very similar to it. It could be off by a constant multiple. So let's do one example. I've got 2 on the next slide, but we'll just do one. All right, so let's do the first one up here. So I have a composition. So it looks like I should let u be the 3x squared, but I'm going to check it first. So here's my thought process. If I let u be equal to 3x squared, then the derivative of that is 6x dx. All I have outside is an x, but it's only off by a constant multiple, so I'm okay. So that's my little thought cloud. It's a constant multiple off, so I'm good to go. So now I'm formally going to write all this out. So I'm going to let u be equal to 3x squared, and then du is going to be 6x dx. I'm taking the differential. And now I'm going to start to make some substitutions. The 3x squared is going to be 3x squared. However, I don't have a 6x dx, so what I'm going to do, if I can get these colors to work, there we go, is divide my du by 6. Here's why I'm going to do that. I've got an x dx left over, so I want to make this equation look like x dx. So I'm going to divide both sides by 6 to make that happen. 1/6 du equals, that's a u, equals x dx. And now I can substitute in. So the x and the dx will turn into a 1/6 du. The cosine just stays a cosine. And the 3x squared turns into a u. And now I have something that I can integrate. That'll become 1/6 sine of u plus c. And my final step is I substitute back. What was u? U was 3x squared. So 1/6 times sine of 3x squared plus a constant. And there's my final answer. We can do the other one in class if we want to, on Tuesday or Thursday. Okie doke. Let's move on. I want to show you also what you can do with limits of integration. So we are going to do one more example. Okay. When I have a definite integral, okay, it's going to be very important to keep track of whether you are working with u's or whether you are working with x's. All right. You cannot plug an x value into a u. The way this stands, these are x values. If you do a substitution, there are two ways to handle this. One is to do it the way we just did it, but make sure that you substitute back to get everything in terms of x's before you substitute in. I'm going to show you another way, though, that's a little bit slicker. It'll make you look smarter in your other classes as well, and that is that you change the limits of integration into u's as well. So I'm going to look at this, and I think that I should let u be equal to 9 minus x squared. The derivative of that is negative 2x. The outside is 7x. It's off by a constant multiple, so I'm good. So I'm going to let u be 9 minus x squared. My du becomes a negative 2x dx. I need a 7x. The 7's no big deal. It can just carry along, so I'll divide by negative 2. So negative 1/2 du equals x dx. And now I'm going to do one more thing. I'm going to take my limits of integration and I'm going to make the same substitution. When x equals 0, u becomes 9 minus 0 squared, which is 9. And when x is equal to 2, u becomes 9 minus 2 squared, which is 5. Now, everything is in terms of u, so I can do my substitution. The 7 I can carry outside. The x dx becomes a negative 1/2 du. The square root is still a square root, but inside the square root I have a u instead of a 9 minus x squared. And now my limits of integration become a 5 and a 9 because I changed them with that same thing. Everything is in terms of u now, so I do not need to change back to x's when I do my integration. When I integrate, I've got a negative 7/2. The u becomes a u to the 3/2 times 2/3, evaluated from 5 to 9. Negative 7/3 times, 27, minus a negative 7/3 times 5 to the 3/2. So it looks like a negative, 27 over 3 is 9, negative 63 plus 7/3 times 5 to the 3/2, and that's about the best I can do without a calculator. Now, your limits of integration do not need to be rectangles. They can be other shapes as well. So let's take a look. I will evaluate this, but I also want to be able to draw a picture of the shape. So if I evaluate it, it's very straightforward. Just like before, I work on the inside and then I work on the outside. Notice my limits of integration have variables, and the variable is different than the thing I'm integrating with respect to. I have a dx, and my limits of integration are y's. And also notice on the outside I have numbers. You should never have variables on your outside integration. They should always be numbers. Let's work this. I just work it like I would normally. So I'll do my inside integration first. So I'm integrating from the square root of y up to y, x squared times y cubed dx. This is telling me that x is my variable. So the y cubed will just carry along because it's a constant. And when I integrate x squared, I get 1/3 x cubed. And I'm evaluating from x equals root y up to x equals y. So I'm plugging root y and y in for my x. So I'll get 1/3 y cubed x cubed minus 1/3 y cubed x to the, excuse me, that's not an x cubed, that's a y cubed. Pardon me. Yeah, I'm putting y in for x, so that becomes a y cubed. And I'm putting root y in for x, so that will become a root y cubed. So I end up with 1/3 y to the 6th minus 1/3 y to the 3 plus 3/2 is 9/2. So notice I integrated out the x. What's left over in my integral? Let's check it. A 1 to 4 and a dy. So my next integral will be from 1 to 4. My new integrand dy, and notice it all matches. Everything is in terms of y, so I can continue the way that I would normally. So I'll go ahead and do that integral as well. So I'll have 1/21 y to the 7th minus, that one I can't do in my head, 1/3 times 2/11 y to the 11/2, evaluated from 1 to 4, and then I'll finish that out, whatever I get. Okay, just remember that you've got to do both of them. And again, I won't do the other one in this video lecture. They do get long enough, so I'll leave that, and if we need to talk about it in class, we will. But I do want to draw the picture of that domain. So if this is the xy axis, and again, the z-axis is coming straight out, so you think about the surface as hovering above or below the screen right now. Let's look at what this is saying. My x value goes from x equals root y, which is the same as x squared equals y, up to x equals y, which is a straight line. Okay, so my function is between x equals root y and x equals y. And my y values go from 1 to 4. Here's where they intersect, 1 up to wherever they hit at 4. So I'm looking at that region right up there. Let's go on to the next slide and get some more practice. What's going to be important for us is also going to be the other direction, how to get the limits of integration. So let's just set up the first one, and again, we'll do the second one in class if we need to. Okay, so there are two ways. I can either do dx first or dy first. So I'm going to do them both. Come back here. If I do this with with dy first, I want to think, with dx first. Let me think a minute. Been a while. dy first. This is dy first. I think from bottom to top where my region is. So I get equations for both of these. Let's see, this starts at the origin. This slanted line looks like it goes up to the point 412, so that's the function y equals 3x. So my region starts at 3x, and it ends at y equals 12, dy. Then my x limits, remember I said my x limits are always going to be numbers, or my outside limits are always going to be numbers. To find my outside limits, I'm going to get the numbers at the extremities here. So this number is x equals 0, and this number is x equals 4. So whatever function I have, if I integrate with respect to y first and then with respect to x, I'll integrate from 3x to 12. dy, and then I'll integrate from 0 to 4 dx. If I want to do the same thing with dx first, I think about how this ranges in the x direction. So this line is the line x equals 0, and this line is the line x equals 1/3 y. It's the same function, right? So I can take what I know and just solve it for x. So if I want to integrate this with respect to x first, I'll integrate from 0 to 1/3 y. And then again, on outside, I look at the extremities. The lowest y value is 0. That's a 0 there, not a 6. And the highest y value is 12. So I'm always looking for extremities. Both of those, depending with my function on the inside, both of those will give me the same answer. But notice my limits of integration are much different. So you're going to think bottom to top for dy, left to right for dx, remembering that outside is always a constant. Let's look at this one. Sometimes integrating in one direction is easier than another. If I try to integrate this with dy first, from bottom to top, is not a problem. Let's see, this is the point 1, 0. This is the point 4, 1. So this function is going to be y equals 0 plus my slope is 1, 2, 3, 1/3 x minus 1. So integrating from this, the bottom of my shape is 1/3 times the quantity x minus 1 up to the top, and this surface is y equals 2, no problem. And then the outside, my extremities are 1 to 4 dx. So integrating with respect to dy first is pretty easy to set up. That's not the easiest function in the world, but it could be worse. Let's go the other way around. I'll get a different color for that. I'm going to erase this. And let's think about what's happening now. If I want to integrate this with dx first, I start at the left, and that's an easy equation. That's x equals 1. And I go to the right. Oh, I have two different functions that cut off the right-hand side. So because of that, here's how I'm going to handle it. I'm going to break this into two pieces. Let me call this one A and this one B. So I'm going to have to do two integrals. Let's look at A. A starts at x equals 1, and it goes out to the slanted line. So I need to take the slanted line and solve it for x. So that's going to give me 3y equals x minus 1, and 3y plus 1 equals x. So that goes up to 3y plus 1. And then my y extremities, it starts at 0 and cuts off at 1. So there's the bottom piece. And the top piece is a rectangle, so it's going to be quite easy. My x value starts at 1 and ends at 4. And my y value starts at 1 and ends at 2. So in this direction, I've got to do two separate pieces because my right-hand side is defined by two separate functions. However, if I did it with dy first, then it's much easier to work. Limits of integration here. Let's take a look. It's a unit circle, so I have x squared plus y squared equals 1. If I do dx first, let me move that over. My x starts at 0, no problem. My x ends at the function, so I'll solve the function for x. So that becomes the square root of 1 minus y squared. And then my dy starts at -1 and goes up to 1. So there's that one. If I do it with respect to y first, let's take a look. Get another color. If I do this with respect to y first, it's the same function at the bottom and the top. What's going on there? Well, let's solve this for y. X squared plus y squared equals 1, so y will actually equal plus or minus the square root of 1 minus x squared. Actually here, this would be a plus or minus also, but I'm over on the side where x is positive, so I only use the plus. I don't need the negative. But now I have both sides of the circle, so I'm going to have a plus and a minus. There's a minus 1 minus x squared up to a plus root 1 minus x squared dy. And then again, my x's are easy. I look at the extremities from 0 out to 1. There's a setup there. Let's set up one more integral. And I think, yeah, that'll be a good place to stop, and I'll make another video with triple integrals. So let's set up but do not evaluate an iterated integral for the volume of the solid below the graph of 169 minus x squared minus y squared and above the plane z equals 69. So we've got to get a little bit of a picture for this. Let's see, if I look at traces on this, my x traces or my y traces look like upside down parabolas. My x traces look like upside down parabolas. From the top, it looks like circles. So this is, come back here. An upside down paraboloid. Looks like that. Okay, z equals 69 is a perfect horizontal plane. So actually, let's draw it here. And when they intersect, I want something below this guy, above that guy. So I need to know what this shape looks like for my limits of integration, and it's a circle. Okay, so my integrand is easy. 169, minus x squared minus y squared minus 69. That's easy. Let's look at a top view. The top view we know is a circle, and the boundary of that circle is going to be where those two surfaces intersect. This boundary right here is that. So I need to set those two functions equal to find out what that looks like. So 169 minus x squared minus y squared equals 69. And if I add x squared and y squared to each other and subtract 69 from each other, I get 100 equals x squared minus y squared. So this is a circle with radius 10. And now I can find my limits of integration. So if I want to do dx first and then dy, I'll solve for x, the left side of the circle. Whoops, that's a plus there. Plus or minus 100 minus y squared equals x. So this is the left side. This is the right side. I work from left to right. So minus 100 minus y squared up to plus square root of 100 minus y squared. And then my y values are easy. They are just the extremities, so minus 10 to 10. And there's our example. And that is a good place to stop. That's been 50 minutes. I'll do triple integrals in a little bit in another video. That'll be a much shorter video than this. So see you later.